Okay, so we'll have a look at another question from the topic of electromagnetism. We're asked, a bubble with mass 0.01 grams floats in air. It has a charge, and it's a positive charge, of 1.6 times 10 to the minus 17 coulombs. We're asked, what is the acceleration on the bubble if it is subject only to the Earth's fair weather field? Okay, so there's a concept in physics known as the fair weather field. Fair weather field. And the fair weather field has a few different values. It has an electric field value associated with it, somewhere between 100 and 300 volts per meter. We're going to say that it's 100. We're going to use the lower bound, but this number can vary depending on who you ask, where you look, what research is done on it, etc. The fair weather field is the normal electric field which occurs on the surface of the Earth on an ordinary day. So the Earth is not completely neutral in terms of fields. There is always some kind of field, and the field that exists just on an ordinary day is about 100 volts per meter. The direction is towards the surface of the Earth. So if we draw the sky and the Earth as two parallel plate capacitors, so we draw an upper part of the atmosphere as being, the upper part of the atmosphere will be positives, and then the lower part will be negatives, and then the field will go down from positive to negative in this case. So this will be upper atmosphere, and this will be the Earth surface. So this field goes down. Now we have a particle floating in air. Let's say that the particle is here. It is positively charged, and that means it's going to go down. So when we're calculating the acceleration, we're going to use a formula to calculate the acceleration. We don't actually care about the positives and negatives in this formula. We know that it's going to go down. So what is the acceleration? It will be a positive acceleration downwards. So we have a formula linking field, charge, mass, and acceleration. We know that the acceleration due to a field on a particle is equal to the field strength multiplied by the charge divided by the particle's mass. So we have the mass of the particle, mb, is 0.01 grams. Well, this is not the SI unit, we need kilograms. So we multiply this by 1,000. So this is, we divide this by 1,000. So this is 1.0 times 10 to the minus 2 grams. So if we divide that by 1,000, it'll become 1.0 times 10 to the minus 5 kilograms. It gets smaller because we're going from a smaller unit to a larger base unit. The charge is already in coulombs. So this is the mass in kilograms, charge in coulombs. Fair weather field, we're not told in the question. We have to assume this. And we're going to assume a value of 100 volts per meter. So this gives us 100 times 1.6 times 10 to the minus 17 divided by 1 times 10 to the minus 5. So we're going to plug this into our calculator. We get 100 times 1.6 times 10 to the minus 17. You could simplify these as you're going along. I'm not going to bother to because I may as well just put them in the calculator. Times 1 times 10 to the minus 5. This gives me 1.6 times 10 to the minus 10. 0.6 times 10 to the minus 10. And this is going to be meters per second squared because it's an acceleration. And this will be going down. So what is the acceleration on the bubble if it's subject only to the Earth's fair weather field? The acceleration is 1.6 times 10 to the minus 10 meters per second squared towards the Earth, so down. And this is the answer we're after. You could factor the positives and negatives in this. You could set your orientation of positive y being up, x to the right being plus x, and then you could do it all and you would end up getting an acceleration that was negative because if you structured the question in a particular way. It's better not to do that. It's better to think about magnitudes, and then from the magnitudes, calculate the value, then think of the direction, right? So you use the formulas to find the number, and then you think about the problem, and you think, well, what's happening? This thing has a positive charge, so it attracts the negative, so it goes down. Because if you did it the other way, if you tried to get the formula to deal with the direction for you, you would have to identify that the Earth's fair weather field in this case is negative, right? That's where the negative direction will come from. So it would be fair weather field is minus 100 because it's going downwards, multiplied by the charge divided by the mass. Better to just deal with magnitudes than think of direction by thinking about the problem.